Good afternoon. Today we will continue talking about the limitations of derivatization due to a free silanol group and how can we deal with this kind of functionality in order to reduce the trouble shoots resulted or raised from this kind of reactivity. If you remember the last time we talked about end capping, and we said that end capping simply is to immerse simple entities such as TMS in order to block the reactivity of free silanols, which cannot be easily derivatized due to the bulkness of the hydrocarbons. But with using small entity like TMS, we can get this kind of silanols capped, and in this case we reduce significantly the reactivity of this kind of functionalities. Another strategy to reduce the reactivity of silanols is to add competitive base to the mobile phase. Once we add competitive base such as triethylamine or diethylamine, okay. Now triethylamine in a neutral pH, it will be ionized. So if we have mobile phase with a neutral pH, now this kind of base will be ionized. So it will interact with the free silanol, okay? And in this case, free silanols will not be available to interact with our analytes. So the big advantage of the competitive base here that this group or this molecule interacts with free silanol group, and in this case free silanol group will not be available to interact with our analyte. In this case we will end up with what? With sharp peaks for the analyte. Okay, so this is a good strategy, and we choose, if you see here, we choose a base without chromophore, and the reason behind that, we don't need UV detector of chromatography. If we use UV, for example, okay, to detect the molecules, we don't want this detector to be overwhelmed with the detection of competitive base. If we have chromophore here, then the sensitivity of UV will be reduced significantly. So definitely when you use competitive base, the two character of base should be available here, that the base should be easily ionized, should be quite basic. The second thing, that shouldn't or should lack the chromophore in order to prohibit any probability for the detector overwhelming by the competitive base detection. Also, we can add ion pairing agent. Ion pairing agent is a detergent which can be added to a mobile phase. Now, one of the good detergents is SLS. SLS is American name for SDS. SDS is a British name. Sodium lauryl sulfate or sodium dodecyl sulfate, the same compound. Now, sodium lauryl sulfate is hydrocarbon of 12 carbon atoms, and we have what? SO3 minus. Okay, this is the sulfonated. Sulfonate, you can write it with F in American style or PH in a British style. So we have sulfonated for 12 carbon. That's why we obtain SLS. Now, this is an ion pairing agent. Ion pairing agent. As you know, it is a surfactant. It has surfactant property. So, ion pairing agent can react with basic analytes. Now, basic analytes in neutral pH, we have them what? Ionized. Okay. Now, once we add ion pairing agent to the mobile phase, so we have it in excess, so all the time it will interact with what? With analyte. Okay. Now, the head here, the basic head, which has a cationic charge, is not available to interact with silanol because all the time it is neutralized with ion pairing agent. We will have a complex formation between ion pairing agent and the basic analyte. Now, the same idea will be occurred not only for analyte, for the standard material. So there's no problem if we have a mixture. We will have the same retention time in comparison with the retention times of reference compounds. In the whole system, we use holistically ion pairing agent for both analytes and their reference compounds. I mean, analyte mixture and their reference compound. So this is a big advantage for using ion pairing agent. We not only we reduce the ionization of analytes, but also we increase the hydrophobicity for the whole compound. We will have a new compound, but it is simply a mixture, or it is ionically built molecule from the basic analytes and SLS or any other kind of detergent. So this new compound is more hydrophobic than the parent compound. So in this case, by using reverse phase column, we will have more higher retention time because it will stay longer in the oily part of the stationary phase. Once we oblige the compound to stay longer in the stationary phase, you will gain better chance for separation and also sharp peaks. So let's say if we have kill peak with retention time 5 minutes without using ion pairing agent for the analyte. Now, after using ion pairing agent, we will have sharp peak maybe at 15 minutes. Okay. If you have another compound, it will be well separated. Now, don't bother about the change of the retention time here because we have a pure material from each of these analytes. So we inject them in the same system. So we compare retention time here. If you have standard material of A with the same retention time, this means that this compound in the mixture is A compound. And we will inject reference material of B if it has the same retention time, this means that this compound in the mixture is B, and so forth. Okay. Now, ion pairing agent has an extra advantage. It is not only forming a hydrophobic complex and reduce the ionization of the analyte, but also it can form a new mechanism of separation over the partitioning mechanism. That, as you know, that C18 hydrocarbon, okay, of ODS, and we have also detergent, which is SLS. SLS will make hydrophobic interaction with what? With stationary phase. And we have also sulfonate head. Okay. Now, this make the stationary phase forming two mechanisms. The first mechanism is partitioning. The second mechanism is cationic exchange. So if we have two cations, for example, to take a simple example, calcium and sodium. So sodium will interact with O minus here, and calcium will interact via two bonds with sulfonate head. So sodium will elute before calcium. Although they are, in terms of partitioning mechanism, they are similar. There is no real differentiation. They are both polar. But this extra mechanism can differentiate this kind of compounds by applying the mechanism which we will discuss later. We call it cationic exchange. Cationic exchange mechanism. It allows cations to be exchanged according to their valency. Okay. Now, you may say that this extra mechanism might not be desirable, such as the salt formation of basic compounds with free silanols. The answer that this mechanism is well controlled, okay, and it will allow all molecules to be accessible for such mechanism in addition to partitioning. So more or less, there is no real difference between some molecules of the analyte comparing with others. All of them, they will be with this under the same umbrella of the effects. So again, we will have sharp peaks, even though we have several mechanisms. To remind you that all molecules from the same analyte under the umbrella of the same mechanisms. Nevertheless, the number of these mechanisms, okay, but entailing due to interaction between the salt formation between the basic compound and the free silanol, that part of minority of the analyte will be affected by free silanols. That's why we have tailing, and we have to solve the problem of tailing as we discussed last time and this time. Okay, so this is one of the strategies to compensate the bad effect of free silanols by using ion pairing agent. Now, we also can remove the excess of metals in the column in order to reduce the reactivity of free silanols. Now, free silanols, as you know, that the source of silica is usually diatomaceous earth, so it is soil more or less, and it might be contaminated with some metals such as calcium, magnesium, and these things. So calcium ion is acidic, while calcium zero is basic. Now, calcium plus 2, according to the lowest definition of acidity, it is acidic. It has empty orbital, so it will accept electrons, pairs of electrons from oxygen. This make electron withdrawing effect from silanol. And once we have electron withdrawing effect, this OH becomes more polarized. The electron cloud between O and H will be dominantly over oxygen due to what? Due to electron absorption. In this case, the acidic behavior of silanol will be significantly enhanced. So the reactivity of silanols will be more, and the pKa of silanols will be 4 or less. Okay. Now, In order to reduce the reactivity, we have to clean, as a company, we have to clean silica from contaminants such as calcium. So once we clean calcium and magnesium and these things, now the electron absorption will be reduced, the acidity of silanols will be reduced as well, and pKa will be above 4. So the chance of reactivity between silanols and basic drugs will be also minimized. So in overall, we have to remove contaminants such as metallic contaminants in order to make the column more suitable for basic compounds. And we call this kind of silica type B silica. So if we have the first contaminated silica type A, so type B silica is type A silica but without contaminants, is more purified, is more suitable for basic compounds. Now I want you to remember this kind of silica good for basic compound from B basic, okay? And if you have ODS column and the silica type is type B silica, so instead of calling it ODS, we can call it BDS. BDS is ODS with type B silica. Is ODS with type B silica. We call it BDS. It is abbreviation of base deactivated silica. Okay, so we remove metals in order to make silica more suitable for what? For basic compounds. So PDS is simply ODS by using type B silica. Now, if you want good column for basic compounds, I prefer to use BDS rather than ODS and use encapped column rather than the one which is not treated by encapper. Okay, and we will stop to this point and later we will continue with the same subject.